Ever wonder how a solar panel works? How it just sits there in the sun and poof, electricity? It feels like magic, doesn't it? But it's not. It's some seriously cool physics. And today, we're diving into the secret behind it all, the photoelectric effect.
So here's the big question, the real puzzle we're going to solve. How can a simple beam of light, something that feels like nothing, actually have enough force to knock an electron right off a piece of metal? Because let's be clear, getting those electrons moving, that flow, that's electricity. All right, to get our heads around this, we have to change the way we think about light. I mean, completely. Forget about light being this smooth, continuous wave, like ripples in a pond. Instead, you need to picture it as a stream, like a machine gun firing these tiny, individual packets of energy. And yeah, these little energy packets, they've got a name. We call them photons. This whole idea was a huge deal, that light could be a particle. So a photon is just one little particle of light, and the energy it's packing is tied directly to its frequency. The formula? It's elegant, it's simple. E equals h times f.
So let's just break that down real quick. The E is the energy, right? That's the punch that one single photon delivers. The F is the light's frequency. You can kind of think of this as its color. And that H? Well, H is one of the universe's magic numbers. It's called Planck's constant.
And there it is. Just look at that number. Seriously, that's a decimal point with 33 zeros before you even get to the 663. It is ridiculously, mind-bogglingly small. And that's a huge clue, right? It tells us we were playing in a totally different ballpark here, a quantum world that just doesn't follow our everyday rules.
Okay, so if we're thinking of a photon as our tiny energy bullet, what's it shooting at? Well, the target is a metal surface, and that surface is just jam-packed with electrons, all just hanging out. So you'd think, okay, bullet hits electron, electron goes flying. Easy, right? Well, not quite. It's not that simple. See, the metal itself kind of holds on to its electrons. It puts up a fight. It's like there's a bouncer at the door, or maybe an entry fee you have to pay before an electron is allowed to leave the club.
And in physics, we call this entry fee the work function. It's the bare minimum energy a photon has to bring to the table just to get an electron off that particular metal. Every metal has a different one. And yep, it has its own formula, where that F naught is the minimum frequency, the threshold frequency, that'll even get the job started.
So what this means is that every single time a photon hits the metal, there's a showdown. It's photon energy versus the metal's work function, and it can only go one of three ways.
Okay, scenario 1. The photon's energy is less than the work function. It's like showing up to a concert with $10 for a $50 ticket. You're not getting in. Nothing happens. Scenario 2. The photon's energy is exactly the work function. The fee is paid, the electron gets kicked out, but it's got no extra energy to actually go anywhere. Still no electricity. But then there's scenario 3. This is where the magic happens. The photon's energy is more than the work function. It pays the fee, and it's got energy left over. And this is the absolute key right here. That extra energy, that change, it doesn't just vanish. It gets converted straight into kinetic energy. That's the energy of motion. So the electron doesn't just get freed, it gets launched away from the metal. And that moving electron, that flow, that's your electric current.
And all of this brings us to one neat little equation that sums it all up. The photon's total energy gets split into two jobs. Part of it pays the work function fee, and whatever's left over becomes the electron's kinetic energy. See? Energy in equals energy out. It's a perfect, beautiful example of the conservation of energy.
Okay, that's the theory. But theory is one thing, right? Let's see this in action with the real-world example. Imagine we've got a metal plate made of potassium. We're going to shine some light on it, and our mission is simple. Do we get any electricity? And if we do, just how fast are those electrons booking it?
So, it's the showdown round 2. But this time, we've got actual numbers. On one side, we've got the energy of the light we're shining. On the other, the specific entry fee for potassium. It all comes down to one simple question. Which number is bigger?
First things first, let's figure out the photon's energy. We'll use Planck's constant, h, the speed of light, c, and the light's given wavelength, which is represented by that Greek letter lambda.
Okay, so we run the numbers, and we get our photon's energy. It's 3.98 times 10 to the minus 19 joules. An incredibly tiny amount of energy, but there it is. That's contestant number 1 in our showdown.
All right, now for the other side. We need potassium's entry fee, its work function. And since that's a known property of potassium, we can calculate it.
And that number comes out to 3.68 times 10 to the minus 19 joules. Okay, the stage is set. We have both our numbers. Let the showdown begin.
And there you have it. The results are in. The photon's energy is 3.98, and the work function is 3.68. It's not by a lot, but it's enough. The photon has more energy, it wins.
So, the photon had enough to pay the entry fee, and it even got some change back. And we know exactly what happens to that leftover energy, right? It goes straight to the electron as kinetic energy, which sends it flying off the metal.
So how much extra energy are we talking about? It's simple math. Just subtract one from the other, and that leftover kinetic energy comes out to 2.98 times 10 to the minus 20 joules.
So now we know how much energy the electron has for moving, which of course leads to the big finale question, just how fast is this tiny little particle actually going?
And the answer is just absolutely wild. We plug that kinetic energy into the formula, and we find out its velocity is 2.55 times 10 to the 5th meters per second. Let me put that in perspective for you. That is over 158 miles per second. Unbelievable speed. All from a single tiny photon hitting a single tiny electron.
And this very interaction, this incredible quantum dance, happening billions and billions of times every single second, that's what's happening inside every solar panel on the planet. It's light turned into motion, turned into electricity. It really makes you think, doesn't it? If this one secret unlocked so much, what other jaw-dropping secrets about how our universe works are still out there, just waiting to be discovered?